builds on oxidation numbers, and that's why I did 2 multiple choice on those. So this question asks, what is the net ionic equation for the following reaction that takes place in an aqueous solution? And it's important to note that net ionic equations only show the reaction that actually took place, so we eliminate spectator ions. And it's also important to remember with our solubility rules that nitrate NO3 with -1 overall charge is always soluble with no exceptions. And the outline of the method that I'm going to use to solve this problem is we have to first rewrite the initial equation so that it's A, balanced, and B, we can see what states each compound is in. And then we'll determine the oxidation numbers because we need to include those in our net ionic equation. And then we'll write out the entire equation with each element being separate. That way it's easier to see which ions actually changed, and we cross out the spectator ions, the ones that didn't change at all. So if we rewrite the equation, we get CrCl3, and because it took place in an aqueous solution, that means that both of these reactants are going to be aqueous. Plus, and I'm going to leave a little space here in case we need to change our coefficients to balance it out. And now we have to recall our solubility rules. So this compound here is going to be aqueous because it's with nitrate, and nitrate is always soluble, no exceptions. But these two are not soluble, so this is going to be our precipitate that's formed, and this is solution. Okay, so sorry I ran out of room a little bit here, but this equation is not balanced because, as you can see, we have 3 chlorines here and 2 chlorines here, so we have to go and we have to balance that out. So I'm going to put a 3 here and a 2 here, squeeze that in, because there's 2 nitrates here, but 3 here, so to get that equal, I'm not going to walk through the entire process because it's balancing equations, but then we also have to put a 2 here and a 3 here. So now that it's balanced, we can determine the oxidation numbers, and we can then write out the entire equation with separate ions and cross out any spectator ions. So in determining oxidation numbers, remember you have to give the more electronegative atom its oxidation number as its charge as an ion. So here, chlorine is more electronegative, so we'll make that -1, but it's times 3, and the overall atom has a charge of 0, so then this will have to be +3, and nitrate has an overall charge of -1, but there's 2 of those, so, and the overall charge is 0, so -2, this has to be +2, so that's equal to 0. And here, chlorine again is the more electronegative atom, so that's going to be -1, and there's 2 of those, so this will have to be +2 so that it's equal to 0. And then nitrate here again has an overall charge of -1, but there's 3 of them, so -3, this will have to be +3 so that the overall charge is equal to 0. So now we can go ahead and we can write out our entire equation, and this will help determine our spectator ions. Okay, so as you can see, nitrate here didn't didn't change at all, so we can now cross that out. And this here changed from aqueous to solid, so we're going to keep that. And we're also going to keep chlorine because that changed from aqueous to solid. However, this stayed the exact same, so we'll also cross this out. And then we can simplify this so that it's, and I'm just dividing each of these by 3 to make it, to put it in its simplest form. Okay, so as you can see, this matches our answer right here, our answer number C, or answer letter C. And we can also, I forgot to tell you this at the beginning, but there's a few simple ways to see right off the bat if any of these answers you know will be wrong. For instance, D is definitely going to be wrong because it says that one of the reactants is solid. However, that completely negates the statement in the question that it happens in an aqueous solution. And it also has a product that's aqueous and a net ionic equation that usually doesn't happen. But you can see from the solid right here that this would not be an answer right away. Also, B definitely would not be suitable because this right here, nitrate, is always soluble, no exceptions. So the fact that it's solid here is completely wrong, and so you can eliminate these two right off the bat, which makes it a lot easier to determine an answer. Okay, so now we're moving on to our free response question, which is multiple parts, and it deals with, or at least this part deals with writing a balanced equation, and a bit of that is predicting it. So that's why I thought it was useful, because I know something that I really struggled with was being able to predict an equation kind of from scratch or from very little. So I wanted to include that in here. And then again, we have our oxidation numbers. That was a very popular topic in my project. So the question asks, a sample of solid iron 3 oxide is reduced completely with solid carbon. So first we have to write the balanced equation, and then it asks us what is the oxidation number of carbon before the reaction and what is it after the reaction. So a few helpful notes. I'm going to come back to this later, but let's keep in mind that reducing agents take oxygen away from a compound and oxidizing agents add oxygen. This we didn't really cover because it's a little bit more outdated. This question is from the 2009 essay. So we don't really say it this way, but it'll make more sense when I come back to it in a little bit. And then, of course, again, our oxidation number rules, which we're going to use here and a little bit here too, actually. And then how we're going to go about this. For this part, we'll first predict the products and, of course, the reactants, but they pretty much give us that. And then we'll write kind of a skeleton equation or a first draft, and then we'll write a final equation to make sure everything's balanced and in a proper state. And then for the second part, we'll determine the oxidation number of carbon before the reaction and after the reaction. So pretty much we will pretty much do what we did in the first and second multiple choice problems. And this response is a combination of the two, or the combination of the two types of multiple choice that we did and the two topics that we covered in multiple choice. So I thought that was a good reason to pick this. Okay, so first we have to determine our oxidation numbers, we have to determine the subscripts for each element based off the oxidation numbers that we know. And so we know, because it gives us this right here, that the oxidation number for iron is going to be +3. And if you were debating whether it's going to be +3 or -3, you know that oxide is oxygen, and that's always -2, except in peroxides. So you have to make iron +3 to balance it out. And then, so we want the overall charge to be 0. So we'll start writing our equation here. If we want something, because we're trying to figure out our subscripts, plus 3 plus something minus 2, because that's our oxidation number of oxygen, equal to 0. And then if we do math, or you can see it's pretty easy to see this is going to have to be 2 and this is going to have to be 3, because 2 times 3 is 6, and then negative 2 times 3 is, negative 2 times 3 is negative 6, and 6 minus 6 is equal to 0. So that means that we know that our initial compound is Fe2O3, and then we also know, because it gave us this, that our other reactant is carbon. And then, like I said, how I was going to come back to this. So reducing agents always take oxygen away. We didn't learn it that way because it's a little bit confusing and a little bit outdated. But if you think about it this way, for iron to be reduced, the oxidation number is +3. So if iron lost oxygen, its oxidation number would have to go from +3 to 0, meaning that it gains electrons, because we always want the overall charge to be 0. But if it didn't have this here, it would have to go from +3 to 0. And when it goes from +3 to 0, it gains electrons. So that's sort of our definition of reduction that we learned. So that's another way to think about it. But anyway, that's how we come up with our products, which is iron by itself, because the carbon took away the oxygen from the iron oxide and is now bonded with that. However, this is not balanced. Like I said, we're going to have like a first draft and then we're going to balance it. So we have to make sure that like there's 2 irons here but only 1 here, so we have to balance this equation. And once we do that, it'll be, sorry for my writing there, but 3 carbons, 2 irons over here, because you have 2 here, since we had to balance our oxidation numbers, plus 3 carbons, or yeah, 3 here. So now we have our balanced equation, and then we're going to move on to part 2. So now we're back to determining our oxidation numbers. Our rules for determining oxidation numbers say that in its elemental state, like our carbon before the reaction, because we have to find the carbon before the reaction and after, when an element, or when a reactant is in its elemental state and it's all by itself, the oxidation number is equal to 0. However, afterwards, the carbon is bonded to oxygen, so we have to change. Now it's bonded to another atom, so we're going to have to change it there. So the oxidation before the reaction is 0, and then after, because we have CO, we know that the oxidation number of oxygen is always -2. So to balance that out, our oxidation number for carbon after the reaction must be +2. It's pretty simple, but if you don't know that by itself the oxidation number is 0, that's a very simple way to get it wrong.